Now, in order to simulate a very large data set, so we can get some interesting benchmarks, we're going to create a very simple data set that has 2 layers for a multi-index, a date layer and a category layer, and some values and some weights. This will allow us to do simple aggregations, including grouped weighted aggregations. And so we can look at our data and then store it in a variety of different formats as a Z standard compressed pickle file, in an SQLite format, in DuckDB format, to a Postgres database, and also to CSV. Now, I'm going to show you the data set, but I'm not going to write this out because some of these actually take quite a bit of time to write out. Specifically, the pandas to Postgres writing is very, very slow. It'll take us in the order of 10 minutes to write out all of this data set, even if we chunk it and also write it per group, and it can even run out of memory. But we're going to look at about 36 million rows, which is large-ish. It's not enormous, but it might be on the large side of some of the data sets that we typically look at in pandas. Maybe 1 order of magnitude larger or 2 orders of magnitude larger, maybe up to 3 billion rows. Might be the largest data sets that we're familiar with looking at before we really reach for other tools. But I would say that 36 is probably reasonable enough, especially since this is being run on a virtual machine. And so I don't think I can actually even generate a data set larger than this in memory. Now, if we take a look at the data, we can see, as we said, we are storing dates, some category value, some values, and some weights. We can see all of this data represented in the CSV format, in Postgres, in our SQLite data set, as well as in DuckDB. And we can even take a look at the data files as they exist on disk, and you'll see that one very interesting detail of DuckDB is, as a consequence of being able to store this data in a typed fashion, the actual underlying storage for the data is quite small. If we look at this, we can see CSV is not particularly efficient at storing this data as raw text. So instead of storing the date as a date times 64 NS, a single integer value, it's storing that date as a sequence of character values. And so if you think about it, 4 for the year, 2 for the month, 2 for the day, and 2 dashes, that gives us a total of 10. It is 10 bytes to store something that's otherwise 1 byte, which is why that CSV data is quite large, about a gigabyte in size. The pickle data is a raw representation of the underlying Python data, and so that's going to be very close to what the raw data would actually take, with a little bit of overhead for some of the pandas mechanisms. And so you can see that's about 697 megabytes, including the Z standard compression, which, by the way, for this random data doesn't really do a whole lot. You can see that DuckDB is actually smaller than the underlying pandas data, despite the pandas data storing the underlying categories as categorical values, and the DuckDB storing this as textual values. You can see here, these are actually being stored not as categorical values. This is the name of the column, not the data type of the column. And so that's worth noting that we can actually get some very good storage out of this DuckDB. And you can see the SQLite, unfortunately, is the worst out of all of these. SQLite is taking 3 gigabytes to store all of this data. I can't quite place why it is that it's taking so much space, other than some details of how SQLite is actually storing these. We might have to investigate that further. But I think that it's fairly reasonable to say that DuckDB does win out in terms of the underlying storage here, and it's likely to be something that is not just some misconfiguration on SQLite for why it's taking so much space. Talking about SQLite, let's see if we can differentiate between DuckDB and SQLite, because we know both of these are tools where we have a database that does not exist separate from our running process. It's an in-process database where we can store the underlying storage of that database in a single file on disk, and then we can perform analyses. And you may have even seen in sessions where we talk about pandas analysis and cases where we need to do things more efficiently in pandas, you might take some pandas data, drop it into SQLite, perform some kind of filtering on SQLite, and bring it back up into pandas. And that's a trick that I've seen before for doing operations, especially on very large data sets where they're not exactly too big, but they're nearing the maximum memory that you have, or where they may be slightly larger than the maximum memory you have, but you can get it down to the memory that you have. You can get it into something that you can store in pandas with just a little bit of faceting. So you let SQLite do a little bit of the faceting, maybe some intelligent faceting. Well, here you can see that we can take a look at the underlying data set that we have. And one of the things about SQLite is that it's not really typed. SQLite traces its trajectory through the TCL line of programming languages, where everything is more or less a string that's interpreted in different ways, even though when we look at the schema here, it'll tell us timestamp, text, integer, real, and it will check for those things when I try to insert. at its core, this SQLite data is really textual data. And as a consequence, I can do things like do a substring on the date column without necessarily a conversion. Or if I want to ask this date column what is its year, I do that with a string formatting operation. Whereas in DuckDB, I can still do this operation that asks, give me the first four characters of this string, but there's an implicit string conversion that's happening here. This is first being converted to a string or to textual data, and then I'm performing this operation on it. And if I actually want to grab the year, I don't have to do a string formatting operation. I can do an operation that extracts this. In MySQL, it's called one thing. Here in Postgres and DuckDB, it's called date part. And this gives me actual numeric data back, so I can do things like add 1 to it, whereas here, I'd have to perform another cast in order to, I'd have to perform some other operations to add a 1 here, or you can see here it's being interpreted as a 1 value as a consequence of that string format time. And so there's a little bit of loosey-goosiness to SQLite that I don't get in DuckDB. Do note that DuckDB and SQLite are not mutually exclusive in the sense that you can write SQLite files that can be read by DuckDB. Here you can see the use of a DuckDB extension that allows me to load in this SQLite data and then perform queries on it. And so we could say that if it's the case that DuckDB's benefits, the analytical benefits that we'll see in a moment, are worthwhile, but we have existing infrastructure that makes use of SQLite already, and we don't want to have a very hard migration. We want to have a smooth migration. One thing might be to use DuckDB in order to query the underlying SQLite data sources that you have, and then slowly migrate those over to a more native formulation. Well, we're going to see that analytically, DuckDB is significantly faster than SQLite, but it's worthwhile to point out why SQLite still has a place, not only in our hearts, but also in our work. And if you read through the DuckDB documentation, it will tell you that DuckDB is really about the analysis of the underlying data sets. It's not about the construction of those data sets. It's not about having multiple writers simultaneously writing to the data set. And so to get a sense for what that might look like, I have a very simple benchmark here, where I have a simple table with names and values, and I have 100,000 rows of data that is randomly generated, and I have 2 multiprocessing targets, both of which just write this data into this underlying data set, one for the SQLite data set and one for the DuckDB data set, making sure to do some small things like unlink the file if it already exists and create the table. Well, if I run this code, we'll see that inserting 100,000 rows over and over and over again across 10 different processes takes about 1.8 seconds. If I do this for just one process, let's do this for just one process to see if we gained anything doing this in parallel or if we lost anything. You can see, well, this wasn't particularly fast. There was some contention on this table so that the writers couldn't write at the same time. And so here, if I had multiple tables, we can imagine that if each one of these, for example, did a separate table, let's do this table, and then we'll construct a table name based off of which process it is. And then we'll take the table name in here, and we'll do a little bit of f-string since we can't actually interpolate that otherwise. Here, we could see what this might look like. And of course, we're going to have to do this create a table multiple times. So here, let's quickly create all of our tables. So we have that. And we can see, OK, if we were to do this for just one process, it's relatively fast. If we do this for all the processes where they're all touching different tables, you can still see there's a little bit of contentions on this file, but it still allows us to do this. If we try the same thing with DuckDB, we will discover that this is actually very slow. In fact, if we try exactly the same thing, it will fail. We cannot write to this DuckDB data set from multiple writers at the same time. You can see there's a lock on disk that is preventing us from writing to this data file from multiple processes. So what we'd have to do is we'd have to write to this serially. And even though there is some contention that's causing this SQLite to be a little bit slower than if, for example, we had 10 different files, you can see that the DuckDB version of this is much, much slower, on the order of about an order of magnitude slower. This will take about 15 seconds or so to run. And so we can think that very much like pandas and NumPy, DuckDB is a tail-end analytical tool once the data already exists, once it's already been collected, once it's already in one place. Whereas SQLite might be a little bit more similar to some of our pure Python mechanisms, what we might use in the process of collecting the data, if not a fuller featured database like Postgres.